First of all, we're going to go through some of the reasons why Polygon CK, what the issues that Polygon zkEVM is solving, how we are using zero knowledge technology on the blockchain to solve these issues related to scalability. And then we're going to extrapolate from that example to take a look into some real world applications where we could use zero knowledge technology to improve current user experiences, improve solutions, or just make something new that doesn't really exist right now, like real world assets tokenization. So we're going to start first with the issues that Polygon zkEVM solves. So as you're probably, if you've been a user in the blockchain ecosystem as a whole, and of course, more specifically, Ethereum, you have probably heard about the high transaction costs to perform actions on the blockchain, to save information on the blockchain, change the state of a smart contract or something related to that. And most of it comes because there's a trade-off of a lot of people want to use Ethereum. A lot of people want to use this super secure, super decentralized solution to that is already locking a lot of value, economically speaking, and also has a lot of stakeholders in it. However, there's always a trade-off when it comes to these blockchain solutions, and I'm sure you probably heard about this the blockchain trilemma. So the idea is that you can only have two out of these three. It's like the classic: is it good? Is it pretty? And is it cheap? You can only have three of those. So it's a similar case in here. So you can have usually decentralization and security, which is what Ethereum currently offers. A lot of decentralization, as we know, it's very easy to mount a node, start validating blocks on the blockchain. You inherit a lot of the security of the Ethereum ecosystem. However, when you try to scale, given this current architecture that Ethereum has, we face these kind of issues. There's a very low throughput of transactions per second, especially comparing it to other real world solutions such as, I don't know, financial transactions as Visa and MasterCard, even just a regular database. The throughput that they have is a lot more than Ethereum because we're trading off some of the scalability for decentralization and security. So here's where Polygon zkEVM comes and scales Ethereum to meet the demand. So what we are doing here in the layer two world, or how we call it, is we're creating a new layer where we can perform a lot of other transactions and do this computation off chain regarding Ethereum mainnet, thus saving us some costs when it comes to saving storage on the Ethereum mainnet, and using all this new layer to compute off-chain these new transactions and increase the throughput that Ethereum currently has by using the magic of zero-knowledge technology to get all this information that is being generated on the layer two and packaging it into a much smaller footprint, and thus saving us money when it comes to storing data on Ethereum, but also inheriting the security and decentralization of Ethereum. Okay, so how do we do it? So this is like a very famous diagram that you should probably have seen when it comes to layer twos. Most of this presentation is also inspired on Jared, who made a great video about this whole process. And well, you can see on the top, there's usually a lot of transactions happening. A lot of people want to use the blockchain. They want to mint an NFT. They want to just create a swap and get some new meme coin for some ETH exchanged. And you have this set of transactions that are being all the time generated by users. So instead of trying to make all this activity directly on layer one, we already have some this layer two, this blockchain that has assets and has all these equivalent applications, swaps, decentralized swaps. You have lending protocols. You have NFT collections and minters. All of this existing infrastructure on Ethereum can be ported to the layer two because we have the Ethereum virtual machine equivalents on the Polygon zkEVM. So that's first on the layer two side, we have this infrastructure ready to receive transactions. However, once we receive these transactions, we need to get them into the nodes of the layer 2, validate that these transactions are actually valid. This is something that happens already in Ethereum as well. You have to send transactions to a mempool. You get these transactions sorted into a block. You check that the block is valid by reviewing all the transactions and making sure that nobody's trying to place in a transaction that is not valid. For example, you're trying to send assets that you don't really have. That's gonna fail, and that's something that already each blockchain takes care of. But how do we do this translation from the layer 2 to the layer 1? So how it happens in Polygon zkEVM, it's very similar, like I said, to Ethereum mainnet, where we have the submitting of transactions and the executing transactions. However, there's 3 additional steps before going to Ethereum mainnet, which are the steps 3, 4, and 5. Batching transactions, sequencing, and aggregating. And we'll see where the magic of zero knowledge comes specifically in the last step, step 5. So the first 2 steps are very common. You probably have done all of this already. You have sent the transaction. This transaction, for example, in Ethereum mainnet, it gets sent to the mempool. In Polygon zkEVM, it gets sent to the pending transaction pool. And these transactions are living there waiting to be picked up by the sequencer in the case of Polygon zkEVM. And the sequencer takes care of making sure that these transactions are valid. You usually build your transaction when you're interacting with any website. The website takes care of it for you, so you don't have to think about how you have to structure them or anything. And once it's built and sent into a transaction pool, the sequencer checks, as mentioned before, that these transactions are valid. They check your assets, check the gas, that it's well constructed, that, I don't know, it doesn't include any false signature, like all these cryptographic functions that are also included in the blockchain, and make sure that everything is good. And once it's validated, it's propagated within all the nodes. So this is very fast. This happens almost immediately when you submit a transaction into the Polygon zkEVM, into the layer 2, and you get this feedback that the transaction has been executed on the Polygon zkEVM. However, it has just happened on the layer 2. We need to make sure that these transactions are secured by layer 1. Otherwise, it's not terrible that you don't have it secured by layer 1. There are other ways to do it, like Validiums, where you just post, instead of posting the whole batch of transactions, you can just post a simple proof of what happened. But here we are doing this, so it's like an extra layer of security. Since you are posting all the transactions that are happening on your layer 2, anyone can actually rebuild or reconstruct the layer 2 state from one simple proof, because it includes all the state of the layer 2. So what happens is the sequencer not only executes and validates and executes the transactions, it also works a batching of the transactions before sending to the Polygon zkEVM smart contract, which actually lives in the layer 1 in Ethereum mainnet. So how we do it, we need this struct that is defined as so. And the main component of this struct, as you can see, is the transactions field, which is a bytes type. And what we're doing here is, this is just one batch of transactions, and here we can place an amount of transactions. There's a limit. I don't have the number off the top of my head, but the idea is to be able to take a lot of transactions in, realize them, just basically transforming them into bytes instead of these regular objects that we know how transactions look. We serialize them into just bytes, which is very similar to a string. And then we concatenate them or just put them together and put them in just this field of bytes transaction. That's how we package these transactions in just a very small footprint already. But what happens? We have a lot of transactions, and we need to batch a lot of these smaller transactions, but we're gonna still have a lot of batches, right? We're gonna have, I don't know, between 1 and 50 or 60 batches that can be stored within one simple batch. I mean, not just one batch, but like the whole number of batches. So instead of just one, we're gonna have n number of batches, like you can see here. And how it happens, we have our trusted sequencer, which is living in both on layer 2, but also on layer 1. And it interacts with the Polygon zkEVM contract to generate these batches. And here's how it looks. For example, the transactions, once it's serialized and concatenated, it looks like a very large string in hexadecimal. And this includes all the transactions that have been serialized. And they can be, for example, there's an example in another slide that has around 52 transactions in just one batch. And you can have any number of batches, usually around 50, I think also. So you're already scaling 250 transactions per this single interaction between the layer 2 and the layer 1. So once this gets packaged and it's ready to be sent into the layer 1, that's where we get the communication into the smart contract, where all the batch transactions get stored in a mapping in the smart contract, as you can see here. And we use this information on the layer 1 contract, the Polygon zkEVM contract, to do the validation. So right now, we have done on the left side, the validation and execution on the layer 2 node. So we have this we have the trust that what is happening in the Polygon zkEVM is valid. And I mean, as long as it stays there, it's okay. But if we want to get the additional security, we need to do these batching transactions. We are in the virtual state. We're not there yet, but we are getting almost into the consolidated. We are about to get finality for the blockchain. So we need to do this aggregation of sequence of batches to get to the consolidated state. How does this work? And here's where the zero knowledge magic comes into. We have an aggregator which gets called by the Polygon zkEVM contract and is sent all the batches of these new transactions, all these 52 new batches that were generated by the sequencer and were packaged in one transaction to the layer 1, and it sends it to a special state machine you can think of. It's like let's think of it like a black box. Of course, there's infrastructure inside the zero knowledge circuits that are working to generate the proofs. So in the case of Polygon zkEVM, we send the batches of transactions all to the zk prover, which is a collection of secondary state machines. And these machines work together cryptographically and using mathematical functions to generate first a series of Stark proofs. Stark proofs are a specific type of zero knowledge proof that is generated by the zk prover. And we generate several of these Stark proofs, and then we package them all together into one single snark. It's a succinct, non-interactive. I don't remember the other. The idea is just it's a very simple string of data that can be used by any other agent or any other stakeholder within the flow. And we're gonna check in a little bit what we're talking about. Can check for this small footprint, this string of information, input it into the zk prover, and validate that this proof is actually valid, which is what happens on once the aggregator gets a proof generated by the zk prover. It sends it back to the layer 1, to this Polygon zkEVM smart contract, and this proof is stored in the smart contract. As you can see here, this is a function that is called in the layer 1 smart contract, and the call data for this function proof. That's a proof that we are using that we got from the zk prover that validates all of the transactions that we're sending from layer 2 to layer 1. So instead of sending, I don't know, bytes and bytes of transaction, we're just sending one very small footprint, which is just a string, and that string can be used later by the layer 1 to check, in this case, that the proof is valid. And if it is not valid, it's not going to accept it. So I know this zero knowledge technology can feel like black magic at times, and certainly the mathematical part is very challenging. I don't know if you dabbled a little bit on that. It uses things like rings, fields, and it's a little tricky. But at the end of the day, you don't have to worry about that. once you generate a proof, you can just call the role verifier, which is another it's another contract handled by the Polygon zkEVM ecosystem, and call the verify proof function there. And if it doesn't work, like if it's not valid, you send the proof and the input that the external, the third party, in this case us, the zkEVM contract, needs to validate, and it's gonna return a true or false. And that's everything we need on the Ethereum layer 1 side. We just need to know if this proof that was generated by the sequencer and the aggregator and it's been sent to us, we can validate if this proof is real or not. And what's happening in all of this is, at the end of the day, we're saving a lot of gas, because the proof, like I mentioned, you can see it here, it's very small. Let me see if I can zoom in. There we go. Like I said, it's just a string of an alphanumeric string, of course, in hexadecimal form, and that's all that's stored on the blockchain, on the layer 1. You don't need to store any more information. This is all generated, and that's the whole work. That's why we go through all these steps of generating the zero knowledge circuits here to generate these Stark proofs. These Stark proofs are then used and inputted once again to another zero knowledge prover that generates the snark, and the snark is the one that gets where we get the final proof for our transactions that are being sent from layer 2 to layer 1. So this is how it works on Polygon zkEVM, and the final goal is storing a lot of information, a lot of more information, scaling the throughput of transactions on using Polygon zkEVM layer 2 into layer 1 without having to use all the data that we are actually storing directly on the Polygon zkEVM. So what else does the ZK Tech technology offer? We've explored right now scalability, but there's also the potential for privacy and security. So if you can see here, I try to just translate these blocks into a more general or more generic a diagram of how it works. We have this as a service, or it can be your service or backend that gets data from either a database, it can be from the smart contracts, it can be even from an external user that's inputting information into a KYC form in your website, and it can take that data and input it into zero knowledge infrastructure. Like I mentioned, unless you want to really build these circuits yourself, which is super fun, but it's also can be very challenging. So you can think of them as a black box. There's already quite a lot services that are available, even with just using APIs, where you send the information as an API call into a specific endpoint that, I don't know, for example, Axiom can use, and they return to you the proof with the information, and you can then use this proof and this ID that they generate for you. And with the ID, you can store it once again in your database, and the proof send it to either the third party that's been interacting with you, or store it as well in your database. And you can serve it once again together with the ID, and give it to any third party that wants to validate it, and send this information, which contains nothing but an ID for the proof. That's just an identification for the infrastructure for zero knowledge, and the zero knowledge proof, which is just a string that doesn't give you anything, just a random alphanumeric, or at least it looks like that. But if you input that once again into this machine, it can return you a true or false state, and that way you can validate very quickly if a proof is valid or not. So some simple ideas that come off from here. Like I mentioned, KYC and identity are pretty obvious. You can just input any information into the zero knowledge infrastructure and generate a proof for specific data that you want to validate. In case of KYC, you may want to know if the person is perhaps a resident of the country where you are developing your infrastructure. Let's think about a financial institution, and they need their users to have, their customers to have either nationality or residency. So you can just ask for your users, your customers, to input the information regarding their credentials, and store you can store everything, of course, if you want, but generate the proof for all this information in just one string. And this string can already tell the user if they have, for example, a certain age, if they have residency, they count with the required permits or the required documents. It can be a green card. It can be in Mexico, it's an FM3. Can be any information that you need. Identity, very simple. Instead of showing off your license, your driver's license, which includes personal information other than your age, or just proving that you actually can drive, you have a license, you have a permit, you could just issue a proof with an NFC, and they could scan it and validate if that NFC card is a valid permit. Coordination for systems such as voting systems, where you not only need to keep the privacy of who's voting, but also storing the vote in a private manner in such a way that it doesn't show in the public record what the users are voting until the last part, where you can just use the zero knowledge infrastructure to validate not only that the vote is valid, that is being issued by a valid user or a valid voter, but also like kind of unveiling what the vote actually was, instead of having them all being placed and available, because this could skew the results of a voting system. Proof of reserves, this is also super important in financial institutions or financial applications, where you may want to prove that you have, I don't know, X amount of money in your wallet, for example, or in your bank account, but you don't want to disclose this, which is your bank account or which bank you are using, what is your account number, all this information. You can just generate a proof that holds this information for you and issue it to anyone who wants to validate it. And ideally, a financial institution has also this kind of infrastructure that allows anyone to query information. Okay, so give me the information for, I don't know, from Mel, who is on this bank, and you can query with the ID that I gave you, which is the ID for my zk proof and my proof, and you can validate that what I'm saying is true. Ownership rights as well. You can think about not only digital ownership, but also real world ownership, where you can store records of who is like a real world, is a real estate. You can get these records stored all on a blockchain or all in a specific centralized system, but you can export or open this system so anyone can validate that these records are actually true without disclosing who is the owner. Or if you want to disclose that you are the owner, you can just send the proof with the ID once again, and you get validated that you are the one who actually owns this real estate or this car or this financial asset. And finally, data integrity, which is something that we are seeing already in the Polygon zkEVM. Not only the scalability issues, but you can reconstruct the whole layer 2 state from a proof by deriving that this proof is correct and doing like an inverse step. I mean, of course, this takes a more specific approach on the not only a zk prover, but you need to also translate all these zero knowledge proofs into actual data. But you can do this. You can do this with the zero knowledge technology. And once again, at the end of the day, it's just a matter of inputting data and getting a proof and storing this information. You can store it in a centralized manner in a database, or you can store it directly into a blockchain. And this way you solve not only the issues regarding that the blockchain is public and everything is open for everyone. You can also solve issues for privacy and integrity, that what you are storing on the blockchain is actually valid, and without disclosing the information of what is actually being stored, unless you, of course, want to give some information. You can think also of medical records. For example, for a hackathon, I developed an electronic health prescriptions, where I was storing only the information for the medicine that was for the actual medicine that was required, that was public, so anyone could see it. But the proof that was associating all the patient's information, their age, their other ailments, their record within the electronic health record, that's only disclosed, and it's only giving you the information if this is a user who actually owns this prescription. Sorry. So yeah, this is some ideas that you can start thinking about with zero knowledge technology. There's a lot of infrastructure that can be used right now, a lot of services that don't require you to build the whole zero knowledge circuits. And this is advancing each and every day faster and faster. For us in Polygon, zkEVM, it's helping us scale better. It's helping us keep a level of security of the blockchain of the layer 2 using Ethereum mainnet as base layer. But you can start using it in a lot of different ways. It's a matter of you exposing yourself to this technology, playing around with the circuits, playing around with the APIs that already serve this kind of infra, and just finding out how you can use it to better improve the experience of your users, and also maybe even create new services or new business models that rely on this technology. And yeah, that's it for the presentation. Any questions? Be happy to answer.
Ask questions, please come forward to the laptop and ask it here. I'm going to ask the first question, is like trivial, but I think it's a question people might wonder, so I'll ask this basic question. So is it fully equivalent? So like the expressivity of the zkEVM, EVM, and then like, so for example, can you even like, previously you couldn't like run this CATSAC 256, you couldn't run certain hash functions. So when you tried to port into the zkEVM, they wouldn't run. And so is it like now fully equivalent? Can you just tell us that?
It's not fully, no. There's still, I think, 2 or 3 opcodes, like you mentioned, that are still specifically some that are related to cryptography, which is hard to recreate the circuits for them. But 99% of the use cases for blockchain, for the Ethereum virtual machine, are applicable in zero knowledge EVM, in the zkEVM from Polygon. So yeah, that's a great question. I can share with you the resources where we have the latest stage of our equivalency. For purposes of builders, it's usually a yes, but there's like a small asterisk. There are just 2 or 3 opcodes that have not been fully ported.
Right. Anyone, please come forward and ask the question here.
Hello. So I wondered if you could comment a bit on the kind of latency. So my understanding of kind of proving infrastructure is that, you know, sort of it's something like 100,000 times slower. So what's the kind of latency through the whole process, and what does that imply in terms of how you are batching operations, and what's the requirement on sort of the independence of the operations on the state of the individual batches?
Yes, that's a good point. The current architecture that we're using on the zero knowledge prover, which is this part of the diagram, it does take quite a while to generate the proofs because we're not doing just one proof. We're doing several proofs within the circuits. The finality for this is 1 hour. I mean, it's around 1 hour. It can be a little bit less, a little bit more, but it's usually the time that it takes. So what does this mean? It's as I mentioned, like finality is of 1 hour usually. So technically, there could be like you're not secure within 1 hour of like fully secure, fully consolidated within 1 hour of being your transaction being executed on the layer 2. So this is how long it takes. However, if you're operating on specific things on the layer 2, you can pretty much, I mean, you cannot withdraw. You still need to have this 1 hour withdrawal period as well. So there's this latency that's happening for the Polygon zkEVM. I don't think there's yet a faster way to do it. A lot of work is being done right now on zero knowledge tech. Ideally, we want to bring this down, but it's still a work in progress for sure.
Yeah, the question.
Any other?
Yes, the fact that in the presentation you were talking about like the data going to a smart contract, and I was wondering if you plan to use the blob like EIP 4844.
Got it. I cannot answer to this question personally. I'll definitely to get it for you. As far as I know, there's no work that has been announced by the team. Maybe that's something a little more internal. That's a very good. However, it's something that definitely is very appealing to scale the number of transactions that can be stored or transacted within each batch or each collection of batches that is being sent between layer 2 and layer 1. But I don't know if we have plans at the moment. I have not that I have read about. I'll check that for you because that's definitely something that I've seen been mentioned in other ecosystems, and blobs are still kind of new and not they were maybe not planned for when the first iterations of the blockchain with the Polygon zkEVM was being worked on. But if I get some data on this, I'll share with you. Anyone else?
Yeah, sure. Hi there.
Hey.
So I may have missed a little bit. You were mentioning sequencers earlier. Do you still have sequencers whenever you have the zkEVM once you've gone past? As I kind of understand, you're moving away from validiums. Maybe I've misunderstood. So the question would be, do you still have the sequencers? I guess you might have, according to this picture. And what will be done in terms of making those decentralized? Because I'm guessing at the moment, for like a testnet, you'd have them just very much centralized.
Okay, that's an interesting
sense?
architecture. Yes, it makes sense totally. The sequencer decentralization, it's something that's very discussed right now. I don't think anyone has really cracked. I think maybe Aztec has done like the most work regarding sequencer decentralization. As far as I know, there's no official announcement for this for Polygon zkEVM. We're still depending, and this is a point of centralization, as you mentioned. We're depending on this piece of infrastructure that's living on the layer 2 to communicate with the layer 1. So yeah, this is something that's still being explored, and at the moment, there's no answer that I can give you regarding what's the real plan in the future. But I'm sure that it's something that we need to address eventually if we want to keep this idea of decentralization. And especially, we've seen it happen before. If the sequencer fails, well, you get issues. Another blockchain forgot to fill the gas for one of the sequencer contracts, if I'm not mistaken, and the whole blockchain stopped for a while. So that's something that you definitely don't want to depend on. And it's still a very nascent field that no one has cracked yet, but it's just a matter of time. As the faster we move with the zero knowledge technology, there's probably more ways to look into this problem and remove the centralization of this piece.
All right, thank you. Is there anything you want to just add at the end? Like any people want to build on Polygon, where should they go? Like for like technical implementation, support, grants, any final words you would like to share? If you want, that's up to you.
Yeah, definitely. I deleted the slide for that. Sorry about it. So you can go to Polygon.technology. You can have there. I'll just share it here so we can. So you can get started here on the documentation. And there's also, we have some faucets that you can get test tokens if you want to start building on Polygon zkEVM on the testnet, of course.
You have to change which screen you're sharing, probably.
Oh, sorry about it. I thought I had selected the correct one. 1 second. Okay, gotcha. Here we go. Okay, it's loading the faucet. It's faucet.polygon.technology. Just taking a little bit to load here. And you can start building on the Polygon zkEVM. It's like I mentioned, and was also mentioned by one of the questions. It's fully not fully, but it's EVM compatible and almost EVM equivalent. You really only need to change the RPC, and like I mentioned, 99% of your smart contracts and your existing infrastructure is going to work straight out of the box from Solidity in Polygon zkEVM. Let's see. Yeah, I mean, you can go through this this docs, the full step by step. Recommend using some. I don't know why this is taking so long. Some existing how do you call them? Here we go. So you can get here the test tokens, and you can start using some existing frameworks. I don't know, Scaffold ETH2 is one that I like a lot. You can start using WAGMI, start using Ethers with this, and just change the RPC into Polygon's what do you call Polygon zkEVM KEVM chain information, chain ID, and RPC, and start the building on Polygon. You can also apply to our guilds that we have in Dabl.club, and also we have some funding grants and other kinds of programs for builders, where you can start. If you have a business idea, you have a startup, you have some proof of concept or MVP that you want to show, you can come in here and apply. These are open right now for zk Builder DeFi grants in specific. And we are constantly adding more. If you are looking for grants or looking to build something, let us know. We are building the Dabl Learn platform, and we are also finalizing the Dabl Bootcamp, which is going to be launched within the next month. And then if you don't have knowledge regarding how to get started with Polygon, how to build something with the front end and start integrating smart contracts, you can also take that. And yeah, that's what we have at the moment. Do let us know if you are interested in building something else. We have run some other grants already, and there's going to be more coming. There's already a tour for developers, and yeah, that's it for me. I don't know if you want to take a look into something else. We'll be happy to review.
Excellent, that's amazing. So thank you so much for giving this virtual talk and for answering the technical questions. We're gonna share this talk online later. Thank you so much for joining.
No, thanks for inviting me, and I hope you have an excellent day.
Bye-bye.